Natural physics is a concept astrophysicist LeRoy developed that explains in down-to-earth scenarios how the principles of physics could have come about from observing nature. Each episode begins with a scenario, followed by an example to illustrate the application of these principles in futuristic research at the frontiers of science, such as LeRoy's astrophysics doctoral research, and then concludes with an exploration of how these same principles could have very well been used by ancient cultures and civilizations. Mathematics is naturally encountered and incorporated as the exciting and fun tool of science that it is. Science is the window into our amazing world of nature, and mathematics is the tool to open that window. Natural physics encompasses current, futuristic, and ancient physics, and ties them together by the principles of physics that are common threads running throughout each.
Greetings, I'm LeRoy, and welcome to the Natural Physics Experience, live from Costa Rica. Last week, there was a definite delay between the audio and the video. Interesting effect. Made me feel like I was broadcasting maybe from the ISS, the International Space Station, right? And there was that delay. Okay, let's pick up where we left off, all right? We had gotten out that toolbox. Remember the toolbox? Remember that toolbox, right? That contains all of our mathematical tools that we've been using to track the betatron oscillations of the protons around the synchrotron at Fermilab, okay? This is a review, but again, we had analytic geometry, which is a combination of algebra and geometry, okay? We had trigonometry. We had calculus, differential equations, partial differential equations, boundary value problems, okay? And now we started using another tool called linear algebra, which involves matrices. Okay, all right, our mathematical toolbox, okie dokie. Okay, we have our matrix that represents a physical quadrupole magnet, all right? And I talked about the analogy with optics, where you're using lenses to guide a beam of light. And in the case of a synchrotron, you're using quadrupole magnets to guide a beam of highly energetic protons, okay? And at the end of the show last week, I introduced the concept of the force constant, K, right? And I talked about how in a spring, that K, that force constant, for example, is a measurement of how tight that spring is, all right? And I also talked about the phase-space ellipse, which is very similar to that spring. So I want to bring the two up together. Okay. First of all, here's that spring that I talked about, okay, where you have an object at the end of the spring. And okay, the coils of this spring, they're a physical expression of the force constant. How tight the coils are or how loose the coils are, okay? That's K, the force constant of this spring. Now, we have to go over here to the quadrupole magnets And there's a force constant involved here as well, okay? That keeps those protons circulating in phase space around the central trajectory down through the quadrupole, okay? We're going to come back to this, but let me switch over to the phase space ellipse that I talked about last week. Okay. You can see that this is an ellipse as opposed to a circle, but it still represents periodic motion, motion that repeats itself, right? And that's called, in physics, simple harmonic motion. I don't know. I like to think of a harmonica, or remember the squeeze boxes that would make a nice sound? Harmonic, harmonious. That's a reach. Anyway, you have an object that's repeating its motion. Okay? It's repeating its motion around a central equilibrium point. So in this phase space ellipse that I drew years ago in this paper, there you have the horizontal axis and you have the vertical axis, okay? And it just shows that as the protons circulate around the synchrotron, their motion in phase space can be represented by an ellipse where the motion repeats itself in the horizontal direction and in the vertical direction, okay? And if you remember the prime, that stands for how much the horizontal and the vertical positions of the protons are changing with their distance down the z-axis, the central trajectory around the synchrotron, okay? This angle here, it's a way of locating where they are along that ellipse. This is trigonometry. And then the square root of beta. By the way, this symbol is called psi. And this is beta, square root of beta. That's the amplitude. Remember I talked about last week how as the protons circulate around the synchrotron and they're betatron oscillations, right? Back and forth, up and down around that central trajectory. Remember I talked about the amplitude, how far they'll go to the left or to the right horizontally with respect to that z-axis. How far up and down they'll go with respect to that central z-axis, okay? Amplitude. So basically, that's what in the equations of motion, the square root of beta in phase space, that is the amplitude. That represents how far, this is the central trajectory right here along that z-axis down the quadrupole, how far the protons deviate to the right or to the left horizontally, how far they deviate up and down with respect to that z-axis. So this is a way of representing how far they'll go. And as you might expect, it's very important to know this. I talked about before how you have physical parameters of the quadrupole magnets. Okay, they have a certain width, height, length. But especially with respect to width and height, you got to make sure that this phase space ellipse, that the square root of beta is such that the protons don't start colliding with the sides or the top or the bottom of the quadrupole magnets. Okay. Okay, back to the spring, physical spring, okay? All right. So it's very important that we are able to calculate how tight or how loose the force constant of the quadrupole magnets are. We got to do that. We got to get a number, right? To track those betatron oscillations in phase space, horizontally and vertically to the central trajectory, we got to know that force constant. We got to know how much, what's the intensity of the quadrupole's magnetic field on those protons. Just like we would want to know how tight this spring is in having this block that's attached to it going up and down, right? Simple harmonic motion. It repeats itself, okay? Isn't it amazing that we're able to make the analogy between a physical spring that has an object attached to it and the magnetic field of a quadrupole magnet, right? But you can't see the magnetic field of the quadrupole magnet. You can see the spring, right, with the object attached to it, but you can't see the magnetic field that's acting upon the protons. It's invisible, but it's just as physical. Oh, and that rhymes. It's invisible, but it's just as physical. It's just as physical an effect as that spring that you can see, okay? The magnetic influence of those quadrupole magnets, they're just like a spring that's attached to these protons that are keeping the protons in that simple harmonic motion as they circulate around the synchrotron. How cool is that, huh? Okay, all right. Okay, then. Okay, so let's get back to those equations, shall we? Yes, let's. Okay, here's our 4x4 matrix that represents a physical quadrupole magnet. Okay, we got that from the equations of motion. All right, okay. All righty then. Now, actually, let me go one more, couple more. There's that face space ellipse that we just got done talking about. Okay, let's go back. Okay, now I talked about using the thin lens approximation, okay? Okay, the thin lens approximation treats a lens as having negligible thickness compared to its radii of curvature and focal length, simplifying the analysis of image formation and ray tracing. Okay, so what we're doing, imagine a system of optical lenses that are being used to focus a beam of light, okay, photons. They have a physical dimension, right? It's a lens, just like in eyeglasses, right? Magnifying glasses, okay? But what you do, remember last week I said sometimes just to get started, you have to make approximations, just to get a starting point. So in optics, in analyzing certain data, what you do is you apply the thin lens approximation where you physically reduce these optical lenses that are made out of glass. You reduce them. You reduce them to a thin filament. And you know I want to use that one. That has the properties of a focusing element, but it doesn't have physical dimensions, okay? It's a thin lens, all right? Mathematical approximation. Yeah, physically, we can never grind down a glass lens to where it's filament, right? Where it doesn't have physical dimensions. But in mathematics, you can do that, okay? And a lot of times it makes things a lot easier. So, thin lens approximation. So, imagine now that we're going to go from a physical optical lens made out of glass, has dimensions, physical dimensions. And we're thin lens approximation, we're grinding it down to a filament, an optical filament. We're going to do the same thing with the quadrupole magnets, okay? We're going to take a quadrupole magnet that has a physical width, height, and length, and we're going to chisel it down to where it's a thin lens, a magnetic thin lens, okay? Can you imagine that? Can you imagine the tools we had to get out of our toolbox, our mathematical toolbox, to do this, right? How cool is it? I mean, this is amazing, isn't it? So, let's get back to the paper and let's look at the matrices that we're going to use in the thin lens approximation for a quadrupole magnet and a synchrotron accelerator, okay? Let's do that. Okie dokie, here we go. All right.